Alright, so this brings us to the binomial series. Let me actually begin by talking about the finite case of this, which is somewhat encoded by Pascal's triangle. So here's a triangle you can write, put 1, and then you put 1, and then add the things above to get the 2. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 2 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And correspondingly, we have these different expansions of a plus b to various powers, right? The coefficients for the expansion are given here. For example, a plus b to the fifth is a to the fifth plus 5, a to the fourth b plus 10, a cubed b squared plus 10, a squared b cubed plus 5, a b to the fourth plus b to the fifth. And so this is Pascal's triangle. Anyway, so we can write that result more compactly. In particular, a plus b to the k is equal to sum n equals 0 to infinity, 0 to k of k choose n, a to the k minus n times b to the n, where here k choose n is actually equal to k factorial over n factorial times k minus n factorial. These same numbers appear in the binomial, in Pascal's triangle above. All right. So you can do some experimenting. Well, let me here. I'll write them in since we're talking about this. So let's see here. Like 5 choose 0. This is 5 choose 1. This would be 5 choose 2. This would be 5 choose 3. This would be 5 choose 4. And this would be 5 choose 5. All right. For example. All right. But we can generalize this a bit and look at a function. Rather than looking at a plus b to the k, we'll look at 1 plus x to the k. Since we know how 1 plus x to the k expands, we can easily figure out what a plus b expands as, because we can just factor a to the k out and look at 1 plus b over a to the k. Alright, so that's, if we can solve this, if we can figure out how to expand that, then we can correspondingly expand a plus b by this little bit of algebra right here. So if we look at f of x is 1 plus x to the k, and then we differentiate, and then keep on differentiating, eventually we'll get to k times k minus 1 k minus n plus 1 times 1 plus x to the k minus n power. And then, of course, if we're looking for the Maclaurin expansion of this, we evaluate at 0. The function, its derivative, its nth derivative, like so. And then plug it into Taylor's formula, and we get this. But this is precisely the same expression as we had up here. Now, the difference between this and that, and technically speaking, this is not quite legit. I mean, I should really only write this equality here when k is a whole number. If k is not a natural number, then this is still true, but this no longer makes sense. Most people wouldn't allow k to be like 3.5, but this expression over here makes sense with k equal to 3.5. So assuming that the remainder goes to 0 anyway, I should, to be a little bit guarded here, I'll put some quotes around that. Anyway, so 1 plus x to the k is this, with the understanding that that is actually so when I say that, I really mean that this is that. All right, to be clear, when k is not a whole number. All right. All right. Well, anyway, nomenclature aside, let's go on and look at some examples. So here's the more complete story. 1 plus x to the k is this, and it converges for x less than 1. But the interval of convergence depends on k. In particular, it can be shown that you include the right endpoint but exclude the left endpoint if your k is non-positive but larger than -1. it includes both endpoints if k is non-negative, and it excludes both endpoints if your k is in fact smaller than -1. So anyway, let's actually put this binomial series into practice, see how it goes. Example 1, expand 1 over 1 plus x squared. All right. So by the binomial series, that's 1 plus x to the -2. So that means my k is equal to -2. So I do 1 plus kx plus 1/2 k times k minus 1 x squared, and so forth and so on. And so there you go. 1 minus 2x minus 3x squared. Minus 3x, that's a plus. Come on, people. I mean, come on, me. Shouldn't I have a plus there? That's a negative, and that's a negative, I think. So that's going to be positive. I believe that's plus. And then here I've got 1, 2, 3 negatives, so that's a minus. Right? And the next one will be plus, and so forth, all right? And that will be the same as example 6 from a previous lecture, which you'll find on pages that are numbered like this. Okay, anyway, moving on. Example 2, if we look at 1 over the square root of v squared minus c squared, this expression is called gamma in special relativity. It's important to the study of classical mechanics, where the speed of light is, where the velocity is close to the speed of light. Anyway, so that is 1 minus v squared over c squared to the minus 1/2 power. If we let u equal to minus v squared over c squared, we've got 1 plus u to the minus 1/2, which by the binomial series result is 1 minus 1/2 u plus minus 1/2 times minus 1/2 minus 1 over u over 2 u squared, and so forth, which simplifies to 1 minus 1/2 u plus 3/8 u squared. And then putting back what u was, which was minus v squared over c squared, we have the following: 1 plus 1/2 v over c squared plus 3/8 v over c to the 4th, and so forth. Now, in order for this to be legitimate, we need that the absolute value of v over c is less than 1. In other words, that the velocity, the speed v is between, the velocity v is between minus c and c. Yeah. All right. And then next up here, if we have 3 over 1 minus x squared, we can rewrite that as 3 times 1 minus x squared to the minus 1, which is that. And then my k is minus 1, so I get 1 plus ku plus k times k minus 1 over 2, and so forth, which ends up giving me 3 times 1 plus x squared plus x to the 4th plus dot 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 dot. This is not surprising, because that, of course, can be written as a geometric series with radius x squared and initial term in a equal to 3, right? Like I said, alternatively, you could have identified this to be a geometric series with a equals to 3 and r equals to x squared. In fact, I would encourage you doing it that way. But the binomial series is nice to know about in case we have fractional powers, all right? And binomial series has been known to people for a while. This is known to Newton, and it's one of the things he used a lot. All right, so now we have a selection of homework problems which borrow both from Taylor's theorem and from binomial series and from geometric series. I think it's got all of the things that we have learned so far into play. So again, it's from the 6th edition of Stewart. Who knows what edition we're in now, or if we're even in Stewart. I guess we're in Stewart. Well, anyway, your text has problems like Stewart, at least I can say that. F of x equals e to the 5x. Find the Maclaurin series from the Taylor expansion directly. So, in other words, differentiate, differentiate again, keep differentiating until you see the pattern. You can see that the nth derivative of this is 5 to the n times e to the 5x. Evaluate at 0, we get 5 to the n. So my Taylor series gives me 5 to the n over n factorial x to the n. And there you have it. Now, if we already knew the expansion for the exponential, we could just straight plug in u equals to 5x and we get the same thing immediately, right? But I was just following what the text asked us to do with the problem, so that's why I did it. What's the radius of convergence for this thing? Well, if you look at the ratio test, for this one, it's kind of big. The ratio test here, if you do it, it works out to 0, which means the radius of convergence is infinity, and the interval of convergence is the whole real line. All right. Number 11 here, find the Maclaurin series for Cinch. So I think I might have done this already actually. Anyway, so differentiate, plug in 0, plug in 0, plug in 0, plug in 0, get 0, 1, 0, 1. So you can see that the odd derivatives at 0 evaluate to 1, the even derivatives evaluate to 0, so we only pick up the odd terms in the Maclaurin expansion, namely these. And of course the n factorials from, well, in this case 2n plus 1, because we only have the odd. I'm writing this, putting 2n plus 1 here is to make sure that the output is odd, right, because we don't want the even ones. Anyway, again, the radius of convergence can be seen to be infinity from the ratio test. 15, Taylor series centered a equals to 3 for f of x equals to e to the x. So since it's e to the x, it's easy enough to differentiate as many times as you like. Not sure what happened there. I think I'm evaluating at 3, and I've got a residual 0 left in there. I'm going to scratch it out. I'm going to try to scratch it out. There we go. Not sure what happened there, but anyway, evaluate at 3, we get e to the 3 for arbitrary derivatives, divide by n factorial. There you go. That is the Maclaurin expansions for e to the x centered at 3. Now there is a way which I prefer, which is just to start with e to the x, and then to add and subtract 3, which then gives me e to the 3 times e to the x minus 3. Then I can write down that this is equal to that immediately by substitution into the known Maclaurin series for the exponential. And so I derive this without doing any differentiation whatsoever. Next up, we'll use the binomial series to expand the square root of 1 plus x as a power series, and we're supposed to state the radius of convergence while we're at it, so let's get to it. So this is 1 plus x to the 1/2 power, which by the binomial series gives me that. Again, binomial series is 1 plus k plus 1/2 k times k minus 1 plus 1 over 3 factorial k times k minus 1 times k minus 2, you know, quantity cubed, and so forth, which in this case the quantity is x, so it's just that. And there you have it. 1 plus 1/2 x minus 1/4 x squared plus 1/16, because this ends up being a 3, and the 2 times a 2 times a 2 is 8. The 3's cancel, we get 2 times 2 times 2, 2 to the 4th, which is 16. And then, of course, we could write it more generally, if you're willing to use this notation, as I am apparently. 1/2 choose n. Although that, again, I really shouldn't say that. This is a shorthand for the thing I mentioned earlier, and some people would be bothered that I wrote this. As I said, debatable notation, and also debatable spelling. All right, anyway, so the radius of convergence is 1 by the binomial series theorem, and all right. I would say we'll discuss in lecture why the radius of convergence is 1, but that seems unlikely. All right, so now 1 minus x to the 2/3 power as power series. Again, we use binomial series like so, and making a substitution of u equals minus x provides that. So pretty straightforward. There it is. Radius of convergence is 1. Supposed to use the known Maclaurin series to expand f of x sine pi x. So that's just directly what it says. You take the known sine series, plug pi x in the place of x, and then just do an algebra step, which is that this is pi to the 2n plus 1 times x to the 2n plus 1 divided by that, and there you go. It's nice and clean. Now on to problem 33. We have been requested to expand x times the cosine of 1/2 x squared via the known cosine expansion. All right. So there's my x, cosine of 1/2 x squared. So what I do is I take the known cosine expansion and I just plug in 1/2 x squared into that, right? So then, because remember the known cosine expansion, let me just write it over here, add some value. Cosine of u, we know from previous work, is the sum n equals 0 to infinity of -1 to the n over 2n parentheses factorial times u to the 2n. So we're just setting u equals to x squared over 2 to do this problem. Okay, that's the idea. And so doing that, and then working out the algebra, we have -1 to the n, 1/2 to the 2n times 2n factorial down here, and then, you know, x times x to the 4n, which is x to the 4n plus 1. And I just cleaned up things a little bit here. There's the first two terms. There you have it. Next, we're asked to use known expansions to obtain power. I'm fighting with my pages. Stupid whiteout makes these things stick together, you know. Use known expansions to obtain power series for f of x is x squared over root 2 plus x. So what I'm going to do is I'm going to look at that. I'm going to treat the square root piece as a -1/2 type thing. But I got to do some work first, right? So first of all, I start with that. I factor out the x squared. I pull out x squared, pull out a root 2 so that I can rewrite this as 1 plus x over 2 to the -1/2 power. Now that I've got this, I focus on that piece, do binomial, use the binomial series result to expand this with my u as x over 2. And so I get that, which then plugging x over 2 back in, and then multiplying the x squared through gives me that. Pretty straightforward, but you got to have a game plan, right? You don't want to, if you're trying to do the x squared as part of the binomial series, well then you're going to be in trouble, you know. I don't know why you do that, but if you were to try to do that, it wouldn't work. Find the Maclaurin series for cosine of x squared. This one is pretty straightforward. We just really go back to this again. Instead of putting u equals to x squared over 2, we put u equal to x squared, and there's no multiplication by x in the example I'm about to go back to. Right, so we put u equal to x squared, and bam, we're done. If you did put, so you can, I'm saying you could look at the graphs of different things and try to see how they compare to cosine. We'll do that more later. Let me not get into that at the moment. Here's the Maclaurin series for x e to the minus x. So I take the known Maclaurin series for the exponential, plug in minus x to it, and then multiply by x. And out pops that. Pretty nice. Number 47. All right, get over there. Stay in here. Get back where you belong. Find the power series solution of the integral below. So x times cosine of x cubed. Now, I don't know, maybe we could get lucky and do this by integration by parts. I don't know, maybe not. But we don't need to at the moment because we can find a power series solution. And so what I do is I take the integrand, I convert it to a power series using the known Maclaurin expansion for cosine with x cubed substituted. And so then that gives me this power series to integrate, which I do. By the way, it's important to actually multiply the x through and clean it up before you get to this step. Otherwise, you might do something that's not legitimate. Anyway, once we have it nice and clean as a Maclaurin series, then we can integrate term by term like so. And bam, there you go. That's the power series solution to the integral. It's not bad. Not bad at all. Find the power series solution to the integral of inverse tangent of x squared. Now here I go back to our geometric series tricks. We differentiate the integrand to get that geometric series, and then integrate to get back to this. But, you know, f of 0 is, so again, c is 0. Someday I'll find a problem with c non-zero. Anyway, hence that's the integrand as a power series, and we can integrate term by term. I think I've done this before. I hope you're starting to get bored with these. I hope you're starting to understand them. Although I don't think watching me do them is ever going to make you understand them. It's an invitation for you to try to understand for yourself, you know. Problem 59, find the first three non-trivial terms in this e to the minus x squared cosine x via multiplication of known series. Alright, so we know how to find the power series for e to the minus x squared by substitution into the exponential series, right? Which was what? E to the u is 1 plus u plus 1/2 u squared plus dot 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 dot, and I'm setting what? I'm setting u equal to minus x squared. That's how I got this piece right here. Alright? Now the other piece is just this straight up the Maclaurin series for cosine, which you should have memorized sometime soon. And there it is. Then multiply it out, first three non-trivial terms. So I'm looking, you know, what's the lowest order? Well, I got 1 times 1. That gives me a constant of 1. That's the only way to get a constant, is that 1 times that 1. What's up next? Well, looks like quadratics are apparent. So I get 1 times minus 1/2. That gives me a minus half x squared. This times that gives me a minus x squared. So in total I've got a minus 3/2 worth of x squared. And then next up is x to the 4th, it looks like, because 1 times x to the 4th gives me x to the 4th. There's no way to get a cube or a linear term in here. So it's just going to be 1 times x to the 4th, and then 1 times that, 1/2 x to the 4th, and then the product of the x squared terms. When you put all those together, you get 25 over 24. And there you go, first three terms in that. So I hope this helps you see how we do some calculations with power series. It looks like I haven't come across a division of series problem. I would encourage you to look in your text to see how that's done. Next time I'll be looking at Taylor's theorem itself, the proof I mentioned, and also we'll be looking at some somewhat technical applications to specific models and functions. And we'll also look at the graphical aspect of how the Taylor series mimics the graph of a function local to the point of expansion. So that's up next. And then I think after that I have an old test to show you. So thanks.